everyone, welcome to the second part of the 17th lecture in the series Mathematical Methods for Economics. We are discussing limits, and in the first part of the video I talked about the preliminary definition of the limit. Just set up a preliminary definition, and we talked about two-sided limit and how the one-sided limits should exist and should be equal. These are the necessary and sufficient conditions for the limit to exist. We also talked about the different situations where a limit does not exist, right? And now let's take a look at an example from the textbooks, etc. and Hammond, and let's try and see if you have been able to internalize the idea of a limit as I have conveyed it. So if you look at this graph here, the question asks you, if you look at this picture, determine the limit of the function f of x as x tends to a for values of a equal to 2, 3, 4 and 6. So take a moment to think about it. Let's first ask ourselves, what does the function tend to as x tends to 2, as x tends to the number 2. So we are basically here. Now if you see here, as x tends to 2 from the left, the function tends to the number 3, and similarly as x tends to 2 from the right, the function again tends to 3. So you can see here the left side limit and the right side limit both exist and they are equal, and that then is the limit of the function as x tends to 2, which is the limiting value is 3. Now notice here there is this slight twist here, which is actually going to take us to the next topic in this discussion, which is continuity. So I won't get into that, but if you notice here, the value of the function as such is 2 at x equal to 2. Right. So this is actually, I'm not going to get into the details here, but I just wanted you to notice that the value of the function at x equal to 2 is not 3 here, but it's actually 2. But the limiting value is 3. Okay. The next part of the question asks you what is the limit of the function as x tends to 3. So 3 would be somewhere here in between. Yeah, it's right. It's going to be right here between 2 and 4. And you can see here that if I approach 3 from the left or from the right, my function will approach 1, right? So the limiting value will be 1. What about 4? What about a equal to 4? So if x approaches 4 from the left, now here there's going to be a problem, because as x approaches 4 from the left, the function takes on the value half, and as x approaches 4 from the right, it takes on the value 3. So clearly here your left side limit and the right side limit exist, but they're not equal. Okay, so that would mean that the limit does not exist for a equal to 4. Similarly, look at a equal to 6. If x approaches 6 from the left, the function is tending to minus infinity. Again, if x approaches 6 from the right, the function tends to minus infinity. But as we said, like mathematically you can write limit of f of x is equal to minus infinity, but here we say, because we talked in the earlier part of the lecture that the limit has to be a finite value, and a minus infinity is not a finite value. So here we say that the limit does not exist. Okay, so you can write it either way, but the limit does not exist. Okay, so yeah, so you could have written it as limit of f of x as x approaches 6 is minus infinity, but actually the limit does not exist. Okay, that's the convention followed. Okay, now I'm going to walk you through a couple of rules to compute limits, and we're going to be following a particular strategy here. So what we'll do is we'll first develop the rules for computing limits for some very simple functions, and then we will combine these rules with some general rules and try and apply the combination to certain combinations of functions, as I'll show you in some examples that I have prepared for you. So let's start with the rules for some very basic functions, very simple functions. So this is as simple as it could be. Here we have a function which is a constant. Right, it has the same constant value throughout. You can see it has the same constant value c regardless of the value of x, right? So clearly as x approaches a from wherever, from the point is the value of the function does not change. So the limit of the function, which is nothing but c, as x approaches a, is going to be the constant c itself. So for example, if we have a function which is equal to 5, then the limit, so c here is 5, so the limit of 5, whether x approaches 0 or x approaches e or x approaches pi, whichever number you want to take, that is going to stay as 5. Okay. Let's take another function, very simple function again. Here we have f of x equal to x. It is a linear function, as you all know, passes through the origin, and the nice part about this function is that the value of the function is the value of x itself. So whatever value x takes, the value of the function will be exactly the same value as x. So the point here is, if I want to take the limit of the function as x tends to a, because the function is just sort of echoing the value that x takes. So if x is approaching a, then clearly the function will also approach a. So the limit of x as x approaches a is also a for every point a, right? So you just have to substitute x equal to a here, right? Now let's look at some general rules for computing limits, and we will combine these with the rules that we set up for the simple functions, and let's see how these general rules pan out. Then we'll start applying these rules. So to set up the ground for the discussion, let's suppose we have two functions f and g, and these are defined in the neighborhood of a. Again, not necessarily at a. The functions may not be necessarily defined at a, but that's all right. They should be defined in the neighborhood of a. And we have that the function f tends to capital A as x approaches lowercase a, and the function g approaches capital B as x approaches a. Okay. Then we have the first property. Now here I'm not giving you the proofs for these rules, because these proofs hinge on the precise mathematical definition which we are going to develop later. So here you have to take these rules as given. The first rule says that the limit of the sum of two functions is the sum of the limits, right? So the limit of the sum of the functions f of x plus g of x as x tends to a is the limit of f as x tends to a plus the limit of g as x tends to a. So the limit of the sum is the sum of the limits, and because we are given here that the limit of the function f as x tends to a is capital A, the limit of g as x tends to a is capital B, so our result here is a plus b. So it's quite simple and intuitive. Similarly, the limit of the difference of two functions f and g as x tends to a is again the difference between the two limits, and that result here will be a minus b. Okay. Let's look at the next rule. So here we have the limit of the product of two functions. We have the limit of f of x times g of x as x tends to a, and this rule says that the limit of the product of two functions is nothing but the product of the two limits, right? So the product of the two limits is nothing but a times b. So that is going to be your result here. That's going to be limit of f as x tends to a times the limit of g as x tends to a, and that's a times b. Okay, the next one is important, as in the limit of the fraction f of x divided by g of x as x tends to a is, so basically the limit of the quotient is the quotient of the two limits. So that is going to be the limit of f as x tends to a divided by the limit of g as x tends to a, and these values are given to us as a and b, so a divided by b will be our result. But note here that this result holds provided that b is not equal to 0, right? Otherwise we'll get into the territory where things are not defined. Okay, and the final rule that we have here is that the limit of the function f raised to the power p by q as x tends to a is nothing but the limit of the function as x tends to a, the whole thing raised to the power p by q. Now the limit of the function as x tends to a is nothing but capital A, so capital A to the power p by q is the result here. But again we have a rider that a to the power p by q must be defined. Okay, so let's see how we can apply these rules. Okay, so let's apply these rules that we have set up. We have this example here. Suppose now actually this is the same function that I had shown you in the beginning of the lecture. The first visual that I showed you was actually a visual of this function, and you can see here that the answer is as x approaches 3 is 6, if you remember the numbers we took. So we were looking at the behavior of the function around x equal to 3, right? So let's actually mathematically, algebraically calculate this limit. So here we have the limit of x squared minus 2x plus 3. So this is, you can just apply the limit operator to all these three expressions. That is equal to the limit of x squared as x approaches 3 minus the limit of 2 times x as x approaches 3 plus the limit of 3. Right? Now we know that the limit of the product is a product of the limits. So here x squared is a product of x and x. So that's going to be limit of x as x tends to 3 times the limit of x as x tends to 3 minus the limit of 2 as x tends to 3 times the limit of x as x tends to 3 plus 3, because as we discussed, the first rule says the limit of a constant is a constant itself, right? Now what is the limit of x as x tends to 3? As x tends to 3, the limit of x is nothing but 3 itself, right? That was the second rule that we did where the function was equal to x. And similarly 3 times 3, we have 9. Limit of 2 is nothing but 2 itself. Limit of x as x approaches 3 is 3 plus 3. So this gives us 3 times 3, which is 9, minus 2 times 3, which is 6, plus 3, which is, so 9 minus 6 plus 3, and that's nothing but 6. And this is exactly what we got through the graphical analysis. The point here is that, when we looked at the graphical analysis, we were approaching x through that slider from both sides of 3. We were taking on values. But remember, the point here is that is not a very formal, exhaustive way of looking at things, because you might take a value very close to 3, but you can't possibly take all possible values close to 3, because you may take a value close to 3, but then you'll also have infinitely many values which would be closer to 3. So that is a problem, and in that sense, this toolkit that I have given you with all these rules, these are actually quite useful to compute limits algebraically. Look at the next example. If I have a polynomial p of x given by c naught plus c1 x and so on till cn x to the power n, and any real number a, then the limit of p of x as x tends to a is nothing but, so you can just simply substitute for the a value here, which is, so the limiting value is c naught plus c1 a and so on till cn times a to the power n. So the limiting value of the polynomial as x tends to a is nothing but the value of the polynomial function at a, value of the p of x function at a. Okay, so this is another example from Sitzeder and Hammond. The limit, what is the limit of capital A times x to the power n as x tends to a, right? So all you have to do is just substitute a into x and your answer is capital A times a to the power n. Okay, let's look at another example. Now here, this is giving you a fraction, a rational function we have here, which is x squared minus 5 divided by x minus 5, and you're asked to compute the limit of this expression, this function here, as x tends to 6, right? Here we can use the property that the limit of a quotient is the quotient of the limits, as long as your denominator is not 0. So if you notice here, in the limit, the denominator tends to 1, right? So there's no problem here. We can easily apply this rule from our toolkit, and the limit of x squared minus 5 divided by x minus 5 is nothing but the limit of x squared minus 5 as x tends to 6 divided by the limit of x minus 5 as x tends to 6, and that is 36 minus 5. So x squared is 36 minus 5, which is 31. The denominator here is 1. So our answer here is 31. Okay, we have a theorem here, and this is actually a very important theorem. Consider the rational function f of x equal to p of x divided by q of x, where p of x and q of x are polynomials. Now here we are going to distinguish between two cases. For any real number a, if q of a, the denominator at a, is not equal to 0, then the limit of f of x is nothing but f of a as x tends to a. Okay, which is the rule that we had in our toolkit, that the denominator is not 0 at a. But you could have a situation where q of a is 0, but p of a is not equal to 0, right? So the second situation, please look at the difference. The second situation is one where p of a, the numerator at a is still not 0, but the denominator becomes 0 at a. Then we say that the limit of the function does not exist. And here you can look at different examples to see that the limit might be minus infinity, or it could be plus infinity, or minus infinity from one side and plus infinity from the other. But the point here is, because these are not finite numbers, the limit does not exist. Now, note here, if you are already thinking the way I'm going to talk about things, then you're on the right track. There's a third case that you might come across here, which is that what if both q of a and p of a become 0 at a, and that then leads to a 0 by 0 form. We'll just come to that in a bit. But first, let's take an example that illustrates this part B kind of a situation. So let's look at this limit. The question asks you to evaluate the limit of x squared minus 5 divided by x minus 5, right, as x tends to 5. So it's just basically the function from the previous example, except that now x tends to 5 instead of x tending to 6, which was example 3. Now here you can see that the limit of the numerator as x tends to 5 is 20, because that's going to be 25 minus 5, right? But the limit of the denominator is limit of x minus 5 as x tends to 5, that is 0. And in this case, as we just talked about in the theorem, in this case we say the limit does not exist, because basically this is going to involve division by 0, and as x tends to 5, the function will shoot off to infinity or minus infinity. In fact, here if you have done the details of limits, if you can note for yourself here that as x tends to 5, the numerator will be 20, but as x tends to 5 from values of, because there's an x squared in the numerator, does not matter, but as x tends to 5 from values of x larger than 5, then the denominator will be positive, but as x tends to 5 from values of x less than 5, suppose let's say 4.9999, then you are going to deal with a denominator that is negative. So in that sense, the left side limit would be going to shooting off to negative infinity. But the point here is that whichever side you look at, the limit does not exist. Okay. Right, and this is the kind of example, the third kind of situation I was trying to get you to focus on, which is where you're asked to calculate the limit of x squared minus 25 divided by x minus 5 as x approaches 5. And in fact, this is a visual that I showed you in the second example in the beginning of the lecture. Now, what do you see here? This expression actually, if you take the limit of the numerator and the limit of the denominator, this expression boils down to 0 by 0 form, which is also known as an indeterminate form. We'll do details of indeterminate forms in the next video. But the point here is that here we have a 0 by 0 form. So can we find the limit? And actually there is a trick here. We can manipulate this expression so as to be able to evaluate the limit. And you can notice here that yes, the function is not defined at x equal to 5, because the fraction collapses to 0 by 0 form. However, if x is not equal to 5, do you notice here that x squared minus 25 will have a common factor here, which is x minus 5. So x squared minus 25, because x squared minus 25 becomes 0, and x minus 5 also becomes 0 as x tends to 5. So there's a common factor. So the numerator x squared minus 25 can be written as x minus 5 times x plus 5 divided by x minus 5. And this then, the x minus 5 factor will get cancelled in both the numerator and the denominator, and this then gives us x plus 5. But note here that this function, this fraction is equal to x plus 5 for x not equal to 5. right? There's a distinction here because if you take this fraction as reducing to x plus 5 throughout, then it will be a straight line throughout. But if you remember the visual that I showed you, the second visual that I showed you in the beginning of the video, you can scroll back to that, there we had a hole in between. So for x equal to 5, the function is not defined. There's a hole at x equal to 5, that point on the graph. But for all other values, the graph is going to mimic the graph of this straight line x plus 5, and that is why you had this graph which looked like a straight line except for that hole there, right? So here then the limit then algebraically boils down to the limit of x plus 5 as x tends to 5, and that is nothing but 10, and that's exactly what we found out graphically in our visual in the beginning of the lecture. Okay, and I'll do one more example to basically be able to illustrate these rules. So this is the case where you're asked to compute the limit of square root of h plus 1 minus 1 divided by h. Now here the trick is, the trick that we can use is to, we can rationalize the numerator. And by the way, where we have these 0 by 0 forms, here also you can see that if we put h equal to 0, we'll have a 0 by 0 form in the numerator and denominator. So here also we have an indeterminate form, and we have this rule called L'Hopital's rule, which again we'll do in a later lecture. So there's quite a lot of stuff to do here. This is just an introductory lecture for limits. So just keep watching, and you'll warm up to the whole idea of limits and the calculations. So here you can see the strategy that I'm going to follow is I'm going to rationalize the numerator, right? So I'm going to multiply both the numerator and the denominator by square root of h plus 1 plus 1, and that then gives me an h in the numerator, right? And in the denominator I have h times square root of h plus 1 plus 1, and that the h terms get cancelled. Remember that this is valid for h not equal to 0, because you can't have a 0 in the denominator, and h greater than or equal to minus 1. And this then, once we reduce things to this format, then I can easily substitute h here, right? Because the denominator does not go to, we have a non-zero limit in the denominator. So I can substitute h equal to 0. We have the limit of the quotient being the quotient of the limits, and that will give us 1 by 2. Okay. And finally, for this lecture today, we'll quickly discuss limits at infinity. Basically, when we talk about limits at infinity, the idea is to understand what happens to a function. What does a function tend to as x approaches infinity or minus infinity, right? And because here, let me state at the outset, because here the function, we are looking at the value of the limiting value as x tends to infinity or minus infinity. Here we can't have a two-sided limit possibly, because we can't have, if x tends to infinity, we can only look at a left side limit, or if x tends to minus infinity, we can only look at a right side limit, right? So that we can just look at one-sided limits here. Right, so let's suppose f is defined for arbitrarily large positive numbers, and let's suppose as x tends to infinity, the function tends to capital A, right? So the limit as f of x, the limit of the function f of x as x tends to infinity is capital A, and let's suppose that as x tends to minus infinity, the function tends to capital B. So the limit of the function as x tends to minus infinity is B. So here these are illustrated in this picture that I have for you. Look at this picture. So you can see here as x tends to infinity, the function approaches capital A, and as x approaches minus infinity, the function approaches capital, the value B, right? Now note here that these horizontal lines, y equal to A and y equal to B, these are also known as horizontal asymptotes. So we talked about vertical asymptotes. Vertical asymptotes basically mean that the function shoots off to infinity or minus infinity as x approaches the line which corresponds to the vertical asymptote. Horizontal asymptote basically looks at how the function behaves as x tends to infinity or minus infinity. There's a subtle, there's a difference here, so you must understand this. So you can see here that the lines y equal to A and y equal to B, these are our horizontal asymptotes. this is a horizontal asymptote, y equal to a is a horizontal asymptote as x approaches infinity, and y equal to b is the horizontal asymptote of the graph of the function as x approaches minus infinity. Okay, let's see how we can calculate limits at infinity. So you have this expression here, 3x squared plus x minus 1 divided by x squared plus 1. Now intuitively, if I ask you what does this expression, what does this function tend to as x approaches infinity or minus infinity? So let's take things one step at a time. So if x is a very large number, you can intuitively see that in the numerator, it's going to be 3x squared which will dominate. In the denominator, it's going to be x squared which will dominate, right? And therefore, when I take the limit, the function will behave like the fraction 3x squared by x squared, which is 3. That is going to be the limit. And this is true even if x is a large negative number. Now, mathematically also we can evaluate this limit. The trick here is, the way to manipulate the function is we divide both numerator and denominator by the largest power of the expression in the term in the denominator. So here, anyway, here the largest power is 2, whether it's a numerator or the denominator, but by dividing both numerator and denominator by the largest power of the denominator, that actually gives us a non-zero limit. So that is why the trick makes sense. So anyway, once you do that, you can write this expression as 3. When you divide by x squared, you get 3 plus 1 by x minus 1 by x squared. In the denominator, you get 1 plus 1 by x squared. And you can see here that as x tends to infinity or minus infinity, these expressions 1 by x squared, 1 by x squared in the denominator, these will all vanish, right? And in the limit, you will approach the number 3. Similarly, this is the last example for today's lecture. If I take this function 1 minus x to the 5 divided by x to the 4 plus x plus 1. So here also intuitively you can see here it's minus x to the power 5 which will dominate in the numerator. It's x to the power 4 which will dominate in the denominator as x tends to any large positive or negative number, and therefore in the limit you will be approaching minus x, so that as x approaches infinity the function will tend to minus infinity. As x approaches minus infinity the function will tend to infinity. Right? So let's see how we can analyze things mathematically. Here you can see here that again the strategy is that you divide both numerator and denominator by the highest power of the denominator, which is 4 here, right? Here once you do that, you get 1 by x to the 4 minus x divided by 1 plus 1 by x cubed plus 1 by x to the 4, and you can see here the same, once you apply the limit, again you're going to get minus x, which will give you the same result as we just got intuitively. So this is what I have for you for limits at infinity. There's still a lot to discuss in this particular section on limits, and in the next lecture we will take up the precise mathematical definition of a limit. We'll talk about asymptotes, we have to talk about indeterminate forms, so there's still a lot left, but that's for the next lecture. We're totally out of time. Thank you.